Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Expansion in Eigenfunctions, Orthonormality, Degeneracy and Commuting Observables under the paper Quantum Mechanics. So students, let us see what we are going to learn in this module. In this module, we'll get to learn the concepts of orthogonality and degenerate eigenfunctions. We will study the Schmidt's orthogonalization procedure to construct a new set of orthogonal eigenfunctions from a given set of degenerate linearly independent normalized functions. We will learn the property of a self-adjoint operator which is required to possess a complete set of orthonormal eigenfunctions. We will study the definition of probability amplitudes and learn how to generalize a spectrum of discrete eigenvalues to a continuous spectrum. We will learn the theorems on commuting observables. We shall now study in more detail the properties of the solutions of eigenvalue equations, generalizing the discussion of the specific cases studied in the earlier modules. In this module, we shall study the concepts on orthogonal eigenfunctions, degenerate eigenfunctions, and Schmidt's orthogonalization procedure to construct a new set of orthogonal of eigenfunctions from a given set of degenerate linearly independent normalized functions. We shall also discuss through a postulate an important property of a self-adjoint operator which is required to have a complete set of orthonormal functions for being admitted as an observable. We shall also establish the closure relation given a complete set of orthonormal eigenfunctions and introduce the definition of probability amplitudes. The discussion, which was so far restricted for the observables which possess a spectrum of discrete eigenvalues, will be generalized to a continuous spectrum. Finally, we shall study important theorems on commuting observables. Let us discuss the orthogonal eigenfunctions first. We start by writing the eigenvalue equation in the operator form as operator A acting on psi n is equal to an psi n, where operator A is a linear Hermitian operator representing a dynamical variable. Psi n are the eigenfunctions which are square integrable and normalized to unity. That is, inner product of psi n with itself is equal to 1. And an are real eigenvalues. If psi I and psi j are two eigenfunctions of operator A corresponding to the eigenvalues ai and aj, so that operator A acting on psi I is equal to ai psi I and operator A acting on psi j is equal to aj psi j, so that the inner product of psi I and operator A acting on ket psi j is equal to aj times inner product of psi I and psi j, and the inner product of operator A acting on psi I with ket psi j is equal to ai times the inner product of psi I and psi j. Taking the difference of the two, we get ai minus aj into the inner product of psi I psi j is equal to 0. Clearly, if the two eigenvalues are not equal, that is, ai is not equal to aj, it follows that inner product of psi I and psi j is equal to 0 for I not equal to j. Then the eigenfunctions belonging to different eigenvalues are said to be orthogonal. Next we discuss the degeneracy. In case there is more than one linearly independent eigenfunction of equation 1 corresponding to one eigenvalue an, then the eigenvalue is said to be degenerate. The degree of degeneracy depending on the number of such linearly independent eigenfunctions. Suppose alpha is the degree of degeneracy of the eigenvalue, so the corresponding eigenfunctions can be labeled with r is equal to 1, 2 and so on till alpha, and we have operator A acting on psi n r is equal to an psi n r, where r is equal to 1, 2 and so on till alpha. You will learn various examples of degenerate eigenfunctions. A familiar example is the set of spherical harmonics Ylm of theta phi, which form the orthonormal set, and these are the eigenfunctions of the angular momentum operator L square. So, L square, operator L square acting on Ylm of theta phi is equal to h cut square into L plus 1 into Ylm of theta phi. Here, the eigenvalues are only dependent on L and independent of the quantum number m. Now it is known that n can have the values ranging from minus L to L, that is, it has 2L plus 1 values. It therefore gives 2L plus 1 different eigenfunctions for each value of L, and consequently the eigenfunctions are degenerate, having 2L plus 1 as the degree of degeneracy. Dimensions are known to have degenerate eigenfunctions of the Hamiltonian operator. Another common example is hydrogen atom, which is in the excited state. It has also degenerate eigenfunctions of the Hamiltonian operator. Next, we proceed towards Shimon orthogonalization procedure. In general, the eigenfunctions belonging to a degenerate eigenvalues are not orthogonal. However, given a set of linearly independent normalizable functions, it is always possible to construct a new set of mutually orthogonal functions by using what is known as Shimon's orthogonalization procedure. Starting from the function psi n1, we write the sequence phi n1 is equal to psi n1, phi n2 is equal to a21 phi n1 plus psi n2, phi n3 is equal to a31 phi n1 plus a32 phi n2 plus psi n3 and so on till phi n alpha is equal to a alpha 1 phi n1 plus a alpha 2 phi n2 plus a alpha 3 phi n3 plus so on till psi n alpha, where aij denote the coefficients which are to be determined such that each function of the sequence is orthogonal to all the preceding ones. From the orthogonality requirement, integral of phi n1 star into phi n2 dr is equal to 0. We deduce using equation 7a and 7b that a21 times the integral of phi n1 star phi n1 dr plus the integral of phi n1 star psi n2 dr is equal to 0. Since phi n1 is equal to psi n1 is normalized to unity, we get a21 is equal to minus of integral of phi n1 star psi n2 dr. Having determined the coefficient a21, we obtain from equation 7b a function phi n2 which is equal to minus of integral of phi n1 star psi n2 dr into phi n1 plus psi n2, which is orthogonal to phi n1. Now, from the two orthogonality conditions, the integral of phi n1 star phi n3 dr is equal to 0 and integral of phi n2 star phi n3 dr is equal to 0, We deduce in a similar way A31 plus integral of phi n1 star psi n3 dr is equal to 0 and A32 into integral of phi n2 star phi n2 dr plus integral of phi n2 star psi n3 dr equals to 0. We thus obtain the relation phi n3 is equal to minus of integral of phi n1 star psi n3 dr into phi n1 plus within the square brackets minus of integral of phi n2 star psi n3 dr divided by integral of phi n2 star phi n2 dr brackets close into phi n2 plus psi n3, which is orthogonal to phi n1 and phi n2 and is normalizable. This process can be continued until we arrive at phi n alpha is equal to minus of integral I going from 1 to alpha minus 1. Phi n alpha is equal to minus of summation over I going from 1 to alpha minus 1 integral phi n I star psi n alpha dr divided by integral phi n I star phi n I dr into phi n I plus psi n alpha and is normalizable. The set of orthogonal functions phi n r for r taking the values 1, 2 till alpha being determined in this way can be normalized through the relation chi of nr is equal to phi nr divided by square root of integral of phi n star phi nr dr, where r takes up the values 1, 2 and so on till alpha. These mutually orthogonal functions normalized to unity satisfy the orthonormality relations, which is integral of chi ns star of r into chi nr of r dr is equal to delta rs, where rs takes up the values 1, 2 and so on till alpha. We have thus shown that it is always possible to construct a new set of eigenfunctions which are orthonormal. Let us assume that this orthogonalization procedure has already been carried out for each degenerate eigenvalue n. Since, in addition, the eigenfunctions corresponding to different n eigenvalues are orthogonal, it follows that all the n eigenfunctions can be assumed to satisfy the orthonormality relation given by integral of psi n prime s star of r into psi n r of r dr is equal to chronicle delta n prime into delta rs. Hence, they constitute orthonormal set. Expressed alternatively, it may be referred as the scalar product of psi m and psi n is equal to delta mn. We next discuss the complete set of eigenfunctions. This is described in the postulate 6. Any dynamical observable represented by a self-adjoint operator having a complete set of eigenfunctions is qualified to be called as an observable. For the case of purely discrete eigenvalues, which we will consider first, we have psi is equal to summation over n Cn psi n. The number of eigenfunctions in the set psi n may be in some cases finite and in other cases infinite. Since all eigenfunctions can be expanded in the set of eigenfunctions psi n, the set is hence said to be complete. The completeness of the set of eigenfunctions of some operators can be proved, but in general it must be postulated. All Hermitians or self-adjoint operators possess a complete set of eigenfunctions. We next discuss the closure relation. The coefficients of expansion of psi is equal to summation over n Cn psi n can be found using the orthonormality relation given by equation 19. Taking the scalar product of both sides of the equation with eigenfunction psi m, we get the scalar product of psi m and psi is equal to summation over n Cn into the scalar product of psi m and psi n, which is equal to the integral over n, which is equal to the summation over n Cn delta mn, and in turn becomes equal to Cm. Considering the case of one particle system, we write explicitly psi of Rt is equal to summation over n into, within the square brackets, integral psi n star of r into psi of r prime t dr brackets close into psi n of r is equal to, I take up the integral sign outside the summation, so is equal to integral within the square brackets summation over n psi n star r prime into psi n of r brackets close psi of r prime t dr prime, and therefore summation over n psi n star r prime into psi n of r is equal to delta of vector r minus vector r prime. We describe the probability amplitude. As we have already defined, the expectation value of a Hermitian operator A for the state described by a wave function normalized to unity, let us expand psi in the complex set of eigenfunctions psi n of operator A according to equation 20 and expand similarly psi star. We then write the expectation value of operator A is equal to summation over m summation over n Cm star Cn into the inner product of psi m with operator A acting on ket psi n is equal to summation over m summation over n Cm star Cn an into the scalar product of psi m and psi n. This equates summation over n the modulus of Cn square an, which is the last step, which equates summation over n modulus of Cn square an, where we use the orthonormality relation presented by equation 19 to get the last step. Since psi is normalized to unity, that is, the inner product of psi with itself is equal to 1, we can also get the relation summation over n modulus of Cn square is equal to 1. We next discuss the probability amplitudes. In view of postulate 5 following Max Born, it is reasonable to interpret that the quantity which is appearing in equation 24, that is P of n is equal to square of modulus Cn, which is also equal to square of modulus of scalar product of psi n with capital Psi, as the probability to obtain in a given measurement the particular value alpha n. Thus, the condition equation 25 may be interpreted to express the fact that the probability of getting some result is unity. The coefficients Cn, which are described by the scalar product of psi n with capital Psi, are called probability amplitudes. Next, we will discuss the continuous spectrum. We have so far restricted our discussion for the observables which possess a spectrum of discrete eigenvalues, as we often encounter observables for which the spectrum is purely continuous or for which the spectrum possesses both a discrete as well as a continuous part. This discussion is therefore not sufficiently general. For example, the momentum operator, which is operator Px, has a continuous spectrum, and the Hamiltonian operator for a particle is an attractive one-dimensional square wheel which belongs to both discrete and continuous spectrum. Suppose we have an observable with a spectrum containing both discrete eigenvalues an and a continuous range of values denoted by the symbol A, and the corresponding eigenfunctions are respectively psi n and psi a. Thus we have operator A acting on psi n is equal to an times psi n, and operator A acting on psi a is equal to A times psi a. Now following the postulate 6, any arbitrary wave function psi can be expanded in the complete set psi n psi a. Thus, operator A acting on psi is equal to summation over n Cn psi n plus integral C of A psi a dA, where the integral covers the whole range of values of A. Observable can be written as expectation value of operator A is equal to summation over n Cm star Cn into the scalar product of psi m with operator A acting on psi n plus summation over m integral dA Cm star C of A into the scalar product of psi m with operator A acting on ket psi a plus summation over n integral dA prime C star of A prime into Cn into the scalar product of psi d with operator A acting on psi n plus into integral over dA prime C star of A prime into Ca into the inner product of psi A prime with the operator A acting on ket psi a. This is simplified to get summation over n Cm star Cn an into the scalar product of psi m and psi n plus summation over m integral over dA Cm star C of A into the scalar product of psi m and psi a plus summation over n integral over dA prime C star of A prime Cn an and the inner product of psi d with psi n plus into integral of dA prime C star of A prime into C of A into inner product of psi A prime with psi a. Wherein simplifying the steps, we have made use of equation 27. Now, if we generalize the result of equation 24 obtained for discrete case, we should have the expectation value of operator A is equal to summation over n square of modulus Cn an plus integral of square of modulus C of A dA. On comparing equation 29 with 30 and using the property, we arrive at the following conclusions. First, all the eigenfunctions belonging to the continuum spectrum must be orthogonal to all those of the discrete spectrum. Second, the eigenfunctions belonging to the continuum spectrum must satisfy the orthonormality condition, that is, the scalar product of psi d with psi a is equal to delta of A minus A prime. The closure relation given by equation 23 for one particle system should be generalized to summation over n sin star r prime into sin of r plus integral psi star r prime psi a of r dA is equal to delta of r minus r prime. Next we move on to commuting observables. Suppose that there are two Hermitian operators, operator A and operator B. If there exists a complete set of eigenfunctions psi n such that each function is simultaneously an eigenfunction of operator A and of operator B, the observables are said to be compatible. Let the eigenvalues of operator A and operator B corresponding to the eigenfunction psi n be respectively an and bn, so that operator A acting on psi n is equal to an times psi n and operator B acting on psi n is equal to bn times psi n. If operator A and B are two compatible observables and psi n is a common eigenfunction, then we have operator A acting on operator B acting on psi n is equal to operator A acting on bn psi n, which is equal to Bn times An psi n, which can also be written as operator B acting on operator A acting on psi n. Since any function can be expanded in terms of the complete set of eigenfunctions according to equation 20, and using equation 34, we find the product of operator A and operator B minus the product of operator B and operator A acting on psi is equal to summation over n Cn into within the brackets operator A, operator B minus operator B, operator A, bracket close, acting on psi n is equal to 0, which proves that commutator of operator A and operator B is equal to 0. Two compatible observables commute. Let us now prove the converse of this theorem, that is, two operators which commute possess a complete set of common eigenfunctions. Consider the simpler case for which the operator A has non-degenerate eigenvalues An. If operator A and operator B commute, it means that operator A acting on operator B acting on psi n is equal to operator B acting on operator A acting on psi n, which is also equal to An times operator B acting on psi n. Therefore, operator B acting on psi n is an eigenfunction of operator A, which is belonging to the eigenvalue An. Since An is non-degenerate, so operator B acting on psi n can only differ from psi n by a multiplicative constant. Let us call it Bn, so that operator B acting on psi n is equal to Bn psi n. This shows that psi n is simultaneously an eigenfunction of the operators A and B belonging to the eigenvalues An and Bn respectively. Let us now consider the case for which An is a degenerate eigenvalue of operator A of degree alpha corresponding to linearly independent eigenfunctions psi and r, where r takes up the values 1, 2 and so on till alpha. Since operator A and operator B commute, so the operator B acting on psi and r eigenfunction belonging to the degenerate eigenvalue An. It follows that operator B acting on psi and r can be expanded in terms of alpha linearly independent functions sin 1, sin 2 and so on till sin alpha. That is, operator B acting on psi and r is equal to summation over s going from 1 to alpha CRS psi ns, where CRS are the expansion coefficients. Suppose we form a linear combination of the function psi and r with alpha constants gr, so that operator B with summation r going from 1 to alpha dr psi and r is equal to summation over r going from 1 to alpha summation over s going from 1 to alpha dr CRS psi ns. Now summation over r dr psi and r is an eigenfunction of operator B belonging to the eigenvalue Bn, provided that summation over r going from 1 to alpha dr CRS is equal to Bn drs, where s takes up the values 1, 2 and so on till alpha. This gives us a system of alpha homogeneous linear equations for the alpha constants gr. This system has a non-trivial solution if determinant of CRS minus Bn delta Rs is equal to 0, where symbol dt stands for the determinant. This is an equation of order alpha for Bn having alpha roots. Corresponding to each root, Bn is equal to Bnk, where k is equal to 1, 2 and so on till alpha is a solution. Thus, the eigenvalue An together with the eigenvalues B and k completely specify a particular simultaneous eigenfunction phi of k of both operators A and B, so that When both operators are considered together, the degeneracy is removed. So students, let us now summarize what we have learned in this module. In this module, we have learned the concepts of orthogonality and degenerate eigenfunctions. We have studied the Shimon orthogonalization procedure to construct a new set of orthogonal eigenfunctions from a given set of degenerate, linearly independent normalized functions. We have learned the property of a self-adjoint operator which is required to possess a complete set of orthonormal eigenfunctions. We have studied the definition of probability amplitudes. We have learned the theorems on commuting observables. Thank you students for your kind attention.